afternoon, everyone. We're staying in space. Today I'm presenting a scientific case study that is in progress on behalf of myself and Diego Maranan, who was supposed to be here, but he's not. Marrick, Braam, Thorsten, Balduin, Oriel, and Jesper, Bruun. Most of the people here on the slide are astronomers. And then me and Diego, we have both a background in art and science. So my own background is in computer science. And, but I'm also a trained visual artist and the co-founder of the SEEDS collective, Space Ecology's Art and Design. Towards the end of the slide, I'll share that website because we just celebrated our 15th anniversary. We've done quite a few projects all over the world since then. So we've drawn a little bit on that experience to present the techniques for the case study that I'm presenting today. However, we stay in pure science, drawing on artistic techniques. So I'm presenting a use case where we do a visualization and interaction techniques for exoplanets, atmospheres. And I'll talk a little bit about three applications that we've explored in here. One, to enhance science communication by using this visualization and engage the audience with quite raw data coming from our models. And then we have an educational application where this was used in an educational intervention, so the same visualization but in a different platform we'll talk about. And towards the end, if there's time, I can hint a little bit at the research we're doing for scientific ideation, how this impacts the scientists that are involved and the professional scientific community that is using this. So maybe a little bit of an introduction on exoplanets. Exoplanets are all planets that are orbiting a star that is not our sun. The discovery and the study of exoplanets is quite increasing rapidly because of specialized tools in space like this. And then obviously the James Webb Space Telescope that I'm sure you've all heard about and have seen beautiful imagery of. They look at quite different atmospheric phenomena. Every tool, every instrument on different satellites has its specific range that it looks at, and there's different detection mechanism, which is revealing quite science fiction-like conditions sometimes. Recently it was discovered that on the exoplanet WASP 107b it rains sand compared to water, but we also have places where there's a whole surface made of diamonds. And traditional these representations of exoplanet atmospheres and their conditions are static and non-interactive, and they pose quite a lot of challenging for public understanding, which leads to a lot of misinformation. In fact, if you engage with the general public and talk about exoplanets, the whole range goes from exoplanets are pure science fiction to we've sent probes to exoplanets and have landed there. Neither of these statements are true. In fact, there's only very few exoplanets that we've directly observed. Most of the exoplanets, we know about 5,000 now, but it's increasing rapidly as James Webb Space Telescope is fully operational, have been detected using quite specific third-party measurements. And so very seldomly is it that we just point a telescope somewhere and can take a picture of an exoplanet. Can you guess why? What makes it so super hard?
Pretty far away.
Yeah, go ahead.
The light of the star nearby?
Exactly. So this very bright star that is shining and beaming in our direction. It makes it really, really hard to take a picture of anything else. But one of the things we do, I don't want to talk too much about detection mechanisms, is what happens is sometimes an exoplanet comes in front of this star. So we measure the brightness of the star and then there will be a small dip because the tiny, tiny exoplanet comes in front of it and we will see a little dip. And then based on how this dip looks like, we make assumptions, calculated assumptions on the conditions on this exoplanet, and we feed that into models. So what my research group does, we don't do observation, we use observational techniques to do storytelling basically, and we feed it into models in order to try to explain basically what has been observed. My fellow colleagues will not still call it storytelling, but I think it is, you take a little bit of information and they come up with very big stories about it that are rooted in something of a reality. And then, as I said, there's quite a lot of rapid advancements with these new satellites up in space. Then the goal was to develop an interactive visual that could be helpful for exoplanetary atmosphere conversations, and explorations. And I had 3 metrics that I set myself out when this project started. I want to have an engagement with the audience in an interactive way. I want to make the actual data explorable by the general public and to have a component for the expert scientists. So I set up the Explore Exoplanets project, which was a combination of a visualization technique, which the ARTIFEX that I'm talking today about, with live action role-playing exercises and interventions. And I've done this 3 times so far at different outreach events. The recent one that I'm presenting today was at an educational conference in Denmark, where I have my office currently. And there we presented 2 platforms. One is a live action role-playing platform that I'll talk about in a second. And then we did our first educational intervention. And so I use the same visual techniques, but one is running in a web platform and the other one is running in an immersive environment. The platform looks for both systems quite the same. So for the data source, we use the actual models from my research group, which is spearheading exoplanet atmosphere detection. 15 of us, 15 PhD researchers and about the same supervisors who are working on this. We use the general circulation models. We have 2 different planets that we can select from. One is Proxima Centauri b, and the other one is a fictional planet. It's a rocky planet, just like Earth, quite similar to Earth, same distance to the Sun, same size approximately, but covered in water. And then we extrapolate 2 variables here. One is wind. In this case, the wind is basically the wind direction, which is either positive or negative, perpendicular to the center of the exoplanet, and the heat. Then we have 2 different visualization techniques on each platforms in 2 and in 3 dimensions, and then different levels of user interactions. And then depending on the platform, there are more interactions that can happen, but I'll talk about that when I hope I can show basically how these platforms work. For the colors, I've used a diverging color palette for the wind heat map to create some contrast, and then a very conventional color map between red and blue for the temperature heat map, because that just feels intuitive and makes it understandable. And then the web platform is customizable for as I said, I do both 2D and 3D representations, and which can help depending on the query that you're trying to solve and what you're trying to find out about these particular planet's conditions. And we use only 1 time frame, so it's a snapshot of the model at one particular moment in time. These models can also alternate in 4 dimensions. But we do have height control, so you can basically select which aspect of the atmosphere you're visualizing, close to the surface or up to 25 kilometers up. So let's talk for a moment about how we integrated this in our live action role-playing games. A live action role-playing game is an interaction in physical space where people assume a character, and based on the characteristics, they will solve a query, a gamified aspect together. It's a gameplay technique which we're exploring for our outreach events. And the way how we set it up, we do 1 pre-LARP, which is our storyline onboarding. It takes 45 minutes, so it's almost as long as the actual intervention. And we have then a character immersion aspect where they train themselves and assume this character that we give to them, but they also alternate between being an ethnographer. And this is where they assume the role of a scientist and they observe the other people playing and take notes. We have 4 acts, and in every act they will make a certain set of decisions, and these decisions will lead to the continuation of the performance, and then by the end we have an evaluation. In our case, the narrative setting that they are in is they are on board of a starship that is moving towards a star system, and they have to make a series of decisions based on that. However, in this storyline, because there needs to be an excuse on how they do not know to interact with this data happens, so the scientific team has been injured during cryosleep is the excuse, and that's how they have to basically start exploring what this data means. So instead of us telling this is what the data means, we give them the data set, we train them how to work with it, and then they can try to find out. However, we do help them. So I This is the technical setup that we do. We have an artificial agent in the ship which works as a Deus Ex Machina tool. So it helps to explain. If the players have a question, they can just call out, just like you know from sci-fi movies, and they get a response through text-to-speech. And then behind the scenes, we both have an Exoplanet scientist who is there, but we also have a bridge with OpenAI through an API. So the company behind ChatGPT in order to rapidly answer questions, because my colleagues are really smart and they know a lot about exoplanets, but not everything all the time. So we draw from different sources in order to respond and interact in real time. We do different light setups and projection mappings to help with the immersion for the people who play this. And as I said, we use the actual data coming from my research group that we're working on. We have 3 different models. Only the last 2 that are presented here are actually being used in the current platform. And this drives the storyline. So the choices that they make, for example, it's which planet looks most promising to colonize for whatever reason, which location, where are the resources, what are the potential dangers, and so forth. And this is something they can explore with using the interface. Then, if you have some time, I'd like to show you a little bit on what that might look like in a simplified version. During the training, we give them this MIDI controller, which just is a super simple way to help them navigate. Voila. So all these buttons have different functions, as I said. You can toggle between the different planets. So now we're on the Proxima Centauri b. This is the non-existing aqua water planet. And then you can choose between the variables. So now we're at the wind. This is the heat. And then you can move basically towards and through the atmosphere. So now we're at 20 meters above sea level, and then it goes all the way up to 25 kilometers. Furthermore, we have, you can select coordinates in order to make your decisions, and then it's all simplified a little bit to note things down, to make the storyline a bit easier, so we don't use actual longitude and latitudinal coordinates, but just map in between 0 and 100. And obviously the 3D visualization can also be navigated in different ways to explore different regions as they go. Then, it's just a little bit different for the web platform. So it uses the same techniques. However, there's a little bit of a difference in visualization. So the platform I just showed runs in Touch Designer. I'm not sure who knows or doesn't know Touch Designer, but it's basically the code base of Houdini that a company Derivative has bought to turn it into a live environment. It's very similar to MaxMSP. It's a for-profit company that runs this. All code should be free. However, it's a really convenient platform, so I gave up on some of my ethics in order to work with it. It's a really good platform and a quite good free tier as well, so I can recommend it. And a lot of this is Python scripting, so on this platform everything is run in real time, so I just use the netc4d file, which is the proprietary file that is the model of the scientist, and I do all of my visualizations in there using a combination of Python and the built-in tools. However, for the web platform, I'm not doing all of that in real time. For optimization purposes, I've processed all of the visualizations and stored it on the server itself, and it just gets accessed for each coordinate, if that makes sense. So I don't generate it in real time, it just lives as an image that gets access, as a memoization, if you're familiar with it. So that the visualization here happens in 3GS, for people who are interested in that. I have it somewhere. So yeah, this is publicly available. It's a little bit rudimentary, but the setup is quite similar. We have a 2D visualization and a 3D visualization. You can change the parameters and the planet that you're on. And you can also change the altitude at different locations. But here it's a bit more scientifically driven. You have the legend there. And in addition to that, you can both in the 3D visualization and the 2D visualization note points of interest so that you can save it in order to resolve basically any queries you have. Because, and this is I think where I'm slowly going to end, we brought together 2 different scientists from my team in order to help with these visualizations and to engage the public. One is Thorsten, who works on protoplanetary disks. So protoplanetary disk is you have your star and your planet-forming material is around it, but the planet has not been formed yet, so it's all cluttering together. And there's a theory that lightning might occur there. However, it's not been proven. Just finished his PhD and couldn't prove it as well. So that's a bit sad, but we used this model and combined it with an atmosphere model from Marrick. And basically what we uncovered is that there is a correlation between heat and the vertical direction of the wind to predict where your chances are for electric fields. And so this is something that for each coordinate, so this graph underneath, it will change per coordinate, as you can see. And it will predict here, for example, that you have a higher chance for electricity generation, and we're now looking into whether that can also use to predict electricity here on Earth. So that would be a super interesting outcome of this intervention. So that's where I'm going to end. To conclude, it has an educational promise. When we ran our interventions, it was quite interesting to get the feedback from the teachers and the students, and it worked well, although there is quite some room for improvement, which is something that we might consider doing. And we've also shared all of the codes with the public as well. And in terms of the live-action role-playing game that we discussed, it really helped to have a platform like this to foster curiosity and exploratory exoplanet atmosphere interactions. So we can refine this platform in the future, hopefully, and make the complex data a bit more engaging for a broader audience. Thank you so much.